Hi, welcome to the ComSci 137 lecture. Sunny here. For this module, we will discuss part 2 of the media access control. Let's start.
In controlled access, the stations consult one another to find which station has the right to send. A station cannot send unless it has been authorized by other stations. The three methods are reservation, polling, and token passing. In the reservation method, a station needs to make a reservation before sending data. Time is divided into intervals. In each interval, a reservation frame precedes the data frames sent in that interval. If there are n stations in the system, there are exactly n reservation mini-slots in the reservation frame. Each mini-slot belongs to a station. When a station needs to send a data frame, it makes a reservation in its own mini-slot. The stations that have made reservations can send their data frames after the reservation frame. Polling works with topologies in which one device is designated as a primary station and the other devices are secondary stations. All data exchanges must be made through the primary device even when the ultimate destination is a secondary device. The primary device controls the link. The secondary devices follow its instruction. It is up to the primary device to determine which device is allowed to use a channel at a given time. The primary device is always the initiator of a session. This method uses poll and select functions to prevent collisions. However, the drawback is if the primary station fails, the system goes down. The select function is used whenever the primary device has something to send. Remember that the primary controls the link. If the primary is neither sending nor receiving data, it knows the link is available. If it has something to send, the primary device sends it. What it does not know, however, is whether the target device is prepared to receive. So the primary device must alert the secondary to the upcoming transmissions and wait for an acknowledgement of the secondary's ready status. Before sending data, the primary creates and transmits a select frame, one field of which includes the address of the intended secondary. The poll function is used by the primary device to solicit transmissions from the secondary devices. When the primary is ready to receive data, it must ask each device in turn if it has anything to send. When the first secondary is approached, it responds with either a knock frame if it has nothing to send or with data if it does. If the response is a negative, then the primary polls the next secondary in the same manner until it finds one with data to send. If the response is positive, the primary reads the frames and returns an acknowledgement verifying its receipts. In the token passing method, the stations in the network are organized in a logical ring. In other words, for each station, there is a predecessor and a successor. Predecessor is a station which is logically before the station in the ring. The successor is the station which is after the station in the ring. The current station is the one that is accessing the channel now. The right to this access has been passed from the predecessor to the current station. The right will be passed to the successor when the current station has no more data to send. This method, a special packet called a token, circulates through the ring. The possession of the token gives the station the right to access the channel and send its data. When a station has some data to send, it waits until it receives the token from its predecessor. It then holds the token and sends its data. When the station has no more data to send, it releases the token, passing it to the next logical station in the ring. The station cannot send data until it receives the token again in the next round. This process, when a station receives the token and has no data to send, it just passes the data to the next station. Token management is needed for this access method. Stations must be limited in the time they can have possession of the token. The token must be monitored to ensure it has not been lost or destroyed. For example, if a station that is holding the token fails, the token will disappear from the network. Another function of token management is to assign priorities to the stations and to the types of data being transmitted. And finally, token management is needed to make low priority stations release the token to high priority stations. In a token passing network, stations do not have to be physically connected in a ring. The ring can be a logical one. In the physical ring topology, when a station sends the token to its successor, the token cannot be seen by other stations. The successor is the next one in line. This means that the token does not have to have the address of the next successor. The problem with this topology is that if one of the links fail, the whole system fails. The dual ring topology uses a secondary ring which operates in the reverse direction compared with the main ring. The second ring is for emergencies only. If one of the links in the main ring fails, the system automatically combines the two rings to form a temporary ring. After the failed link is restored, the auxiliary ring becomes idle again. In the bus ring topology, also called a token bus, the stations are connected to a single cable called the bus. They, however, make a logical ring because each station knows the address of its successor, also the predecessor for token management purposes. When a station has finished sending its data, it releases the token and inserts the address of its successor in the token. Only the station with the address matching the destination address of the token gets the token to access the shared media. In a ring star topology, the physical topology is a star. There is a hub, however, that acts as the connector. The wiring inside the hub makes the ring. The stations are connected to this ring through the two wire connections. This topology makes the network less prone to failure because if a link goes down, it will be bypassed by the hub and the rest of the stations can operate. Also, adding and removing stations from the ring is easier. Channelization or channel partition is a multiple access method in which the available bandwidth of a link is shared in time, frequency, or through code among different stations. There are three protocols: FDMA, TDMA, and CDMA. In frequency division multiple access or FDMA, the available bandwidth is divided into frequency bands. Each station is allocated a band to send its data. Each station also uses a bandpass filter to confine the transmitter frequencies. To prevent station interferences, the allocated bands are separated from one another by small guard bands. FDMA specifies a predetermined frequency band for the entire period of communication. In time division multiple access or TDMA, the stations share the bandwidth of the channel in time. Each station is allocated a time slot during which it can send data. Each station transmits its data in its assigned time slot. The main problem with TDMA lies in achieving synchronization between the different stations. Each station needs to know the beginning of its slot and the location of its slot. This may be difficult because of propagation delays introduced into the system if the stations are spread over a large area. To compensate for the delays, we can insert guard times. Synchronization is normally accomplished by having some synchronization bits, normally referred as preamble bits, at the beginning of each time slot. In code division multiple access or CDMA, one channel carries all transmissions simultaneously. Communication is with different codes. The station receivers use these codes to recover the data for the desired station. It differs from FDMA in that only one channel occupies the entire bandwidth. It differs from TDMA in that all stations can send data simultaneously. Based on coding theory, each station is assigned a code which is a sequence of numbers called chips. To have an idea of CDMA, let us assume we have 4 stations, 1, 2, 3, and 4, connected to the same channel. The data from station 1 are D sub 1, from station 2 are D sub 2, and so on. The code assigned to the first station is C sub 1, to the second station is C sub 2, and so on. We assume that these assigned codes have two properties. If we multiply each code by another, we get 0. If we multiply each code by itself, we get 4, or the number of stations. Station 1 multiplies its data by its code to get D sub 1 times C sub 1. Station 2 multiplies its data by its code to get D sub 2 times C sub 2, and so on. The data that go on the channel are the sum of all these terms. Any station that wants to receive data from one of the other three multiplies the data on the channel by the code of the sender. For example, suppose stations 1 and 2 are talking to each other. Station 2 wants to hear what station 1 is saying. It multiplies the data on the channel by C sub 1 the code of station 1. Because C sub 1 times C sub 1 is 4, but C sub 2 times C sub 1, C sub 3 times C sub 1, and C sub 4 times C sub 1 are all zeros, station 2 divides the result by 4 to get the data from station 1. Thank you.